One of the difficulties in robotics and nature is walking. There are countless videos of babies falling over both on the internet and in people's very own home videos. Learning to walk is a form of optimization. Some animals learn quicker than others, such as horses walking not long after birth. They start off wobbly, but eventually optimize a stronger walk. Within robotics, it would take too much time to program every terrain type and what to do with every sensor reading. This is why self-training and optimization is key for successful robotics, which can be deployed to a range of tasks. Genetic algorithms use random mutations within a genotype, which is assessed using a fitness function. In the case of this problem, fitness being the genotype which walks the best. There are a number of ways to do this and decrease the amount of suboptimal solutions. Here we have a biped chassis using 4 servo motors, an MPU 6050 gyroscope, and an ultrasonic rangefinder. It uses its sensors to assess fitness of each genotype. This robot uses Python 3 on the Raspberry Pi. As a genotype, it will contain a series of instructions to motors. This will be randomly generated angles from a list of choices of 0 degrees, 20 degrees, minus 20 degrees, and 0 will have a higher probability of being chosen to avoid all motors turning at once. If the robot falls over, it will stop performing and set a fitness of 0. A buzzer will sound until the robot is placed standing upright. It will then continue running its algorithm. We have used the microbial genetic algorithm with an initial population size of 30. The microbial algorithm will pick 2 genotypes, perform both, and compare the fitnesses and declare a winner and a loser. The winner will be copied over to the loser. At each step, mutations are applied, where new variations of the genotype will arise to help find new solutions. As seen in the video, the robot initially wiggles and gains little ground due to it measuring a genotype's effectiveness by mainly distance. It will end up cheating the code and walking towards the nearest wall, and that's why we see it turning. This would still be considered successful as it would have gained a form of walking abilities, although it was unexpected. In future versions, there will need to be measures against this. Eventually, the robot will converge on a solution. In this case, shuffling was found to be the best route of travel. We know this not to be the case, so this is a suboptimal solution. Evolutionary strategies are effective at finding a route through a large search space and can indeed do a quicker strategy than brute force. These strategies can still be inefficient due to the random nature of them. In the next version, we plan to use a neural network which is trained via evolutionary strategies. This will help the robot adapt to different situations.